nearly all first semester reactions. What we're trying to come up with is ways that we can group those reagents into patterns that we can then apply outwards and then memorize a little bit less. If you don't like that pattern system, that is entirely fine. You have to memorize it. Okay? Within the spider diagrams, I try to get all of the content I possibly could within those so that you can have access to them. They aren't perfect. Sometimes all the information's there, sometimes it's not. For instance, I can already see right out of the gate, far left, BH3 and THF. Okay? That's not showing the appropriate product. All right? What's wrong? Why? What's wrong with that product? There should be stereochemistry in that product. Okay? If I make that wedged, then hydrogen must be wedged because this undergoes a Syn addition. Okay? Plus the enantiomer. Okay? So the spider diagrams have a lot of information in them. You can feel free to print them out, delete stuff from them, or hide them so that you can practice those. You need to know the reagents. When we hit chapter 13, which is a bit of big news, probably won't be on exam 1, you have to know all the reagents. Right? That's when we really first start synthesis. And synthesis is now how do we make different molecules. Right? That takes a lot of work, and it requires having a pretty quick grasp of all of the reagents. Okay? So into the stuff that I kind of wanted to whip through as fast as we could. Redox reactions, which gets us into chapter 19 a little bit. Actually, not chapter 19 in this case, chapter 24. 19's with oxygen. Okay, when we've talked about reduction and oxidation before, hopefully you've remembered some kind of mnemonic device with electrons, gain of electrons, loss of electrons, all that kind of fun stuff. Okay. The problem with that is that if we take a look at the reaction shown, what happened to the oxidation states? Is it obvious anymore? No. So Gen Chem gave us a nice system that allowed us to manipulate through pretty quickly, but OChem, we need a different system because our molecules are much more complex. In that system, what we will go through and do is focus on where changes were made to the structure, and in particular to which part of the structure. There's a hint, this is an organic chemistry class. Where do we want to keep our focus? In an organic chemistry class. Carbon. So we look at the carbons and see what changed to the carbons. So if we look at this top reaction, we've got a lot of things going on, but ultimately they're all the same. If I compare my carbons across, what changed? Okay. One thing would be to draw on implied atoms, and what you might note is that we gained a hydrogen. Right? At the same time, we lost that pi bond. So we gained a hydrogen. What does that mean? Reduction or oxidation? Oxidation states don't help us. We can go through and come up with other patterns. Reduction is an increase in hydrogen bonds. Did I increase the bonds to hydrogen? Yeah. So it was a reduction reaction. This subcategory of reactions, looking at reduction and oxidation, can again help us with our memorization because we can now memorize reagents as shifting between oxidation states. Okay. If we so chose, as opposed to doing everything else. It doesn't have to be just hydrogen. We can also see it in oxygen bonds, which is ultimately where the term oxidation came from. Okay. A better argument would be to get rid of oxygen altogether and a decrease in electronegative bonds. And in particular, a decrease in more electronegative than carbon. Okay. Oxidation, so we could look at just the oxidation, is now just the inverse. We either increase in more electronegative than carbon bonds, or we decrease in hydrogen bonds. Okay. Either way you want to spin it, those rules become simpler, more efficient, and easier to use than the old Leo Szysgier kind of stuff from Gen Chem. Okay. We could evaluate oxidation states. If you want that, talk to me after class. Okay. For the rest of you, look at the bottom. We've got 6 reactions. Label them as oxidation, reduction, or neither. What changed in the first reaction? Okay. We lost the hydrogen and we gained chlorine, which means oxidation. Next one. Lost a chlorine and gained an oxygen. So I lost an electronegative bond, which would be reduction. I gained an electronegative bond, which would be oxidation. So the net? Neither. What's that? So I've lost a bond to an electronegative atom, or chlorine, which is then a reduction. The end result is I gained a bond to oxygen, which is oxidation. So one is reduction, one is oxidation. The net, the overall for the reaction, is neither. The other way you can apply it is, does it match one of our other chemical reactions, which is really hard to go through and do, and I would just stick with looking at your overall pictures. Bottom one. I lost a bond to oxygen and I gained a bond to hydrogen. This would be reduction. Upper right. Do we see any oxygens changed? Up here. Just hydrogen. Can we look at reduction and oxidation by just looking at hydrogen? Yes. Bottom left is not oxidation. It's reduction. Oh, top right. Okay, you're right. Maybe. What happened? Got rid of this hydrogen and got rid of this hydrogen. Whoops, sorry, circled the wrong one. That hydrogen. What's the result?
Oxidation.
Okay. Lost hydrogens, this is oxidation. Next one down. Okay. Didn't really lose a bond to oxygen. What did I do? Oop, yep, sorry, referencing in the wrong spot. We lost a hydrogen because there were two there originally, and we end up with only one. So I've lost a hydrogen and gained an oxygen. This is oxidation, the last one. We've increased the oxygens a lot, oxidation. Make sense? Huh? For which one? The last one, if we go through and evaluate that, what happened to those two hydrogens? They were lost, so a loss of hydrogen would be oxidation. And then I also gained two bonds to oxygen, which is also oxidation. So everything about that one is an oxidation reaction. So looking at a reaction can help you classify reduction and oxidation. The rest of this section is now looking at those oxidation and reducing reagents. Oh shoot, okay, what was your question?
Bottom left, so you gained a hydrogen, you gained an oxygen,
Mm-hmm.
oxidation, and then did you lose hydrogen? Or you, how long did
Okay. Left to right, what did we do?
you lost the hydrogen to the carbon?
So we lost this oxygen. Loss of oxygen is reduction. And we gained a hydrogen, which is, whoa, gained a hydrogen, which is reduction. Overall reaction is reduction. Where some people get confused is that you might see this hydrogen sitting on that OH. That hydrogen isn't relevant because it's not connected to our carbon. All the chemistry is happening at our carbon. Don't worry about random other atoms. Okay? Other questions? Okay.
So anytime we lose an oxygen, it's reduction period?
Not anytime. We have to be a little bit careful with that. So let's take a look It's going to be a bit weird because I don't want to redraw everything. That reaction is I go from right to left. What did I do to the oxygen bonds?
If we go from right to left,
Yeah.
you would lose the oxygen.
I lost an oxygen.
Yeah.
So we might say, well, that's reduction. But what else did I do?
Gained,
I gained an electronegative atom, which is oxidation. So those conflict with each other. So you can't make the blanket statement, I've lost oxygen, so it's reduction. Okay. That is where the terms oxidation and reduction came from as definitions or as words, but it doesn't apply to the strict chemistry. Okay. Here's another one of those spider diagrams that includes all of the reagents. We will look at fairly in depth in chapter 10 these two reactions, the ring openings of the epoxides. The rest of those we aren't going to look at in so much depth. Okay? We'll look to see how they fit the patterns, the categories we've already talked about, okay? Either being small leaving groups or an electrophile that is also a nucleophile, okay? And see how they match that. Then ultimately you have to know what happens. Okay? And then I'll give you one cheat on all of the cleavages. Okay? I'll give you a cheat method for those. Okay? But the rest, you just have to have these memorized. So when we look at, first and foremost, our ozone, our permanganates, and our osmium tetroxide, really what we've got is a metal surrounded by oxygen, or we have ozone. Okay? In both of those cases, really what we're evaluating is the same basic structure. What charge do most metals have? Partial positive. Our oxygens typically can carry a negative, but with so many oxygens on this structure, one of those oxygens can start to carry kind of a positive aspect to it. That gives us the dichemistry that we need to coordinate to a pi bond, both a negative and a positive. You get the same thing in ozone. You might say, well, but isn't the positive there? Right? So how come ozone still matches this pattern that I'm showing, with a negative oxygen, a positive metal, and a positive oxygen? Can that center oxygen act as an electrophile? What is the definition of an electrophile? What is the definition of an electrophile? Accepts electrons. Can that oxygen accept electrons from an external source? No. Why not? 2, 4, 6, 8. It already has its octet. It can't accept electrons from an external source. Right? This is our best Lewis structure for this compound, but it doesn't show the reactivity of the molecule. To get at the reactivity of the molecule, we'd have to look at our first worst resonance structure, which is a real doozy. Why does this one look so awful? I'm missing an octet on that last oxygen, which means what can it act as? An electrophile. There's the electrophilic positive that can react with my alkene. The electrons shuttle around and form back down. Both of these general cases, what's happening is we're looking at a pi bond breaking. In the metal center, we have a pi bond shifting out to the metal. In the case of the ozone, we have a pi bond going to the center oxygen. Okay. So the leaving group in those cases is a pair of electrons. Is a pair of electrons large? Nope. So all of these reactions then fit under the category of 4+ membered transition states, or 4+ intermediates. Right? In both of these cases, the intermediate is actually going to be a 5 center, because we have the 2 carbons from our alkene, and then we'd have the 3 atoms in our bulk system, okay, or our bulk reagent. Okay, so there's our pi system potentially coordinating and reacting in with it. That does make it a little bit trickier, but really what this is going to focus on is recognizing that we get a Syn addition. Right? Those pieces have to coordinate to the same side of the pi system, which is why when we look in the lower right-hand corner, when we see the metal center ejected, where's the location of the oxygens relative to each other? They're on the same side. By classifying the reagent in this four-plus membered transition, we can recognize that we get a Syn addition. Okay? Same thing happens with the osmium tetroxide. Okay? So it's trying to find that pattern to make life a little bit easier in the memorization part. Okay? This is similar to our Diels-Alder, so similar in fact that Carty includes all of our oxidative cleavage and Diels-Alder in the same chapter. Okay? In the case of the Diels-Alder, it goes beyond a 5-metal center or 5-atom center. We end up with a 6-atom intermediate because carbon can't transfer those electrons quite as efficiently, so we need an extra intermediary. Okay? It's the same basic pattern. Okay? All of these reactions are happening simultaneously in a single step. So we don't get any bond rotation. We're locked into whatever conformations we started as. Okay? So a nice mechanism drawn out by the textbook. Okay, we're going to ignore the predict the product at the bottom because that's kind of a silly question. Okay? Our pi bond comes out, reacts with one of the oxygens, which causes electron transfer up to the metal center, which causes the other oxygen to come back down to interact. Okay? Why would it interact wedge-wedge and not wedge-dash? What's that? Okay. So that's like saying my right hand is on the right-hand side of my body. It's true, but you're using the definition to define your word. Why are the oxygens on the same side of the chemical reaction? Why is it wedge-wedge and not wedge-dash? It's impossible to get wedge-dash. Okay? It is impossible for my right hand to shrink through my body and now poke out my body up the left-hand side. That's not going to happen. Okay? It's a physical effect of that. How do I know that's a physical effect of that? Because I've classified the osmium tetroxide in that reagent of forming those 5+ membered rings. That's what gives me that information. Otherwise, it's rote memorization. Right? Why should we ignore the example for the bottom? It's the same reaction as shown above, literally. Okay. Osmium tetroxide and potassium permanganate will do the same thing. Why would we pick one over the other? What went with osmium tetroxide? Hydrogen peroxide is actually a secondary step, if you notice the far end. That's really it. Osmium tetroxide, maybe a little bit of acid. Okay, relatively minor conditions. What happens when we look at the permanganate? We need a base. Why would I choose osmium versus permanganate? There's a different functional group somewhere in the structure that reacts with an acid or reacts with a base. We're looking at selectivity of our reagents. There's something else in those solutions that's going to cause a different reaction. Minor point when we're thinking about synthesis, but it does happen. We have to watch out for it. It becomes much more important further on down the road. Right? So permanganate will do the same thing. Notice that we have in big bold letters cold, dilute, and base. Why would those all be in big bold letters? Because it needs to be cold. Okay? If you looked carefully enough back at the previous list, the spider diagram, permanganate showed up in 2 places. In one of those places it said cold and dilute. In the other place it said hot and concentrated. Did they result in the same products? No. So we have to be very careful to acknowledge the secondary conditions when we're looking at permanganate. If it's cold and dilute, it directly coordinates just like the osmium tetroxide, okay, and can eventually get cleaved out with the cis diol forming. Okay? don't stress about the first step and don't stress about the product for that one. Okay. So the next part can come into oxidative cleavage. So when we looked at those first initial reagents, all we destroyed was the pi bond. Okay, we got rid of the pi bond, and that was it. We moved to oxidative cleavage, we're now adding a second step. That second step is the breakage of the sigma bond. So it's a full breaking all the way through the structure. Alkenes have a pi bond and a sigma bond. I can do a full cleavage and replace them with oxygens. Because it's a full replacement with oxygens, what type of chemical reaction would this be? Oxidation. What is an alkyne? 2 pi bonds and a sigma bond. What kind of pi bonds? Nonpolar. What was the pi bond in our alkene? Nonpolar pi bond. What does that mean? We get the exact same reactions. Right? So the triple bond will do the same thing as the double bond. Right? We do have to watch out for some of the conditions, and in fact, in this copied image, we have a bit of a problem here. We added some detail here. This is R and R. What does it look like happened in our products for the alkyne? It looks like we picked up some more R's, doesn't it? Okay. We didn't. We only have one R, so what's the other position? Okay. If it's a hydrogen, where did it come from? If you look back to your starting material, are there hydrogens connected to those carbons? No. The only thing we've added here is oxygen. So what is that extra piece? It's oxygen. Okay. So we end up doing a larger oxidative step when we have the alkyne because there's less hydrogens there. Okay? Reagents for this, permanganate will do this. Osmium, then periodate will do this. And then ozone is the other big one. Okay, so ozone and permanganate are the big classic examples. Every so often you'll see reference to periodate doing the same thing. Periodate can't do it on an alkene. Okay, what does it do it on? Can't do it on an alkyne either. What does this step say? It does it on the diol. I have to do the osmium tetroxide, then I can do the periodate. Okay, the periodate mechanism is discussed in the textbook. If you want to look at it, you can look at it there. But ultimately, all of 3 of those reagents are going to go through and completely cleave your nonpolar pi bonds and the sigma bond in between and replace every single one of those bonds with an oxygen. Okay? So they would turn into carbonyls. Is this bottom one just turning into carbonyls? No, so it's not quite right, but it gets the right idea. Okay, and we'll talk about that idea when we look at our cheat here in a second. Our concentrated hot, I really like this sequence of slides, and unfortunately we're not going to talk about it. We'll deal with that later on, because ultimately what I want is that you need to just memorize what's happening with our permanganate. The first thing that happens with our permanganate, okay, so I kind of lied, I do want to talk about it a little bit. We form our 5-membered intermediate. The 5-membered intermediate goes through a cleavage to form the diols. Once we have the diols, permanganate can potentially react again, okay, to get us all the way down to the ketones. Okay? I know that's shown as single mechanistic steps. That's a bit excessive. Actually, no, it's not in this case. I forgot. We get this cyclic internal reaction. The sigma bond breaks to form the pi bond. We break a bond with the manganate, and then we shuttle electrons back down to form the other pi bond. We end up with the structure shown. Okay. Unfortunately, permanganate is a strong oxidizing agent. So if you throw a lot of it at the reaction, and you throw high temperatures at the reaction, a whole nother system happens, and we don't end up stopping at the aldehyde. It continues forward. Okay? It continues forward because of this concept being shown in the upper right-hand corner. We have a carbonyl, which can transition to an acid, hemiacetal, which can transition to an acetal. All of that chemistry is stupidly important, so much so that we will talk about it in great detail in the third unit. Okay? It is what's driving this chemical reaction. Okay? Those carbonyls will react with hydroxide or water in solution to form the acetal. What is important, or in this case the hydrate, what is important about this structure? Name the alcohol forming, which is kind of a silly statement. How would we end the name if it ended with an all? How many of them are there? Two. So it would be called diol. What does our permanganate react with? The diols. So it can coordinate to those, and it can initiate that same cascade of reactions. Whoops. And in the process, I don't remember the mechanism. In the process, cascade it out to the carboxylic acid. So permanganate does not stop at a carbonyl. Okay? It will fully oxidize if it has the opportunity to. Okay? How do we know, or where does it have that opportunity to? What changed in this last step? So just looking at that last step, is it oxidation or reduction? Is it oxidation or reduction? I changed the question. It's oxidation because what?
More bonds to oxygen.
More bonds to oxygen. How do you get more bonds to oxygen?
Remove hydrogen.
You have to remove a hydrogen. Did you lose a hydrogen?
I don't think so.
Did you lose a hydrogen? Yep. There's your elimination reaction. It's the loss of the hydrogen forming your carbonyl. Those eject out there. Kick out the permanganate, we end up with our negative charge. Okay. Neat little dealio, don't stress on it, but that's what ends up happening. Okay. So permanganate, hot, concentrated, oxidize the crap out of it. How do you know you should continue to oxidize? What did we start this off with? Do we have hydrogens that we could potentially oxidize in our starting material? Yes. So you need to remove those in your final product. Okay. You ready for the cheat? Not yet. Sorry, I lied. Come up with the products here real quickly. And by real quickly, if you know the cheat, it should be seconds. So what's our cheat? Take your pi bond and stretch it. Draw it nice and long. Once it's drawn nice and long, finish out the rest of your structure. And now what I'm going to do is erase the middle of the pi bond, and I'm going to replace it with oxygens. Then I'm going to evaluate. Are there hydrogens still connected to those carbons? Yes, I just drew them on. They're in blue. Because permanganate is such a strong oxidizing agent, those get replaced with oxygens. Okay. Can I have just a stable single bonded oxygen? No. What ends up happening? A second step of acid. Sometimes we just run it in straight acid conditions. And what do we pick up? A hydrogen from solution. And we have our final product. Okay. The ACS is fully aware that this is a nice little cheat, which means would we see it drawn that way on the exam? No. How are they going to draw it? Probably in a nice long chain. How many carbons is it? 1, 2, 3, 4, 5. 2, 3, 4, 5. Right? By drawing it out in that straight chain, that can make it more difficult for students to acknowledge what's going on with the system and end up marking it incorrectly. Okay? Other common answers that they would throw in at you? What's the difference? Just a rotation of a sigma bond, so not a big deal. Not true. There's an extra carbon. Okay. In the rush of taking a test, what are the odds that you miscount? Probably pretty high. Any ideas which of these two answers is going to show up first? Probably the red one. Okay? So make sure you count your carbons. As we move through this semester, you will need to be counting carbons and watching out for those as the semester goes, because it's very easy to lose track of them, and we will encounter multiple reactions where a loss of a carbon can make a really big deal.
So what do you do for the cheat again? So you draw a long...
Okay, so I wonder if we had a second example to work with. Let's take a look at the second example. We're going to redraw our structure. It's a little crowded, sorry. It's bugging me. Let me erase all that. Okay, so there's my extra long double bond. Okay, I'm going to draw on all my positions. There's the methyl, right? Now I'm going to go through and erase the middle of that double bond and replace those with oxygens. We'll then evaluate, are there hydrogens that could be turned into oxygens? Okay, that was a good hedged bet. On one side there is a hydrogen there that can get replaced with an oxygen and ultimately the H. The other side, not there. Common answer that you would see on the multiple choice test, the diacid, where people just delete the carbon. You can't get rid of the carbon. You're only getting rid of hydrogens. Okay? Kind of makes sense? So oxidative cleavage, stretch your pi bond, erase the middle out of it, replace them with oxygens, you're good to pretty much run. Okay? No. You can talk to me after class and we can look at the mechanism in a little more detail. Okay? Two more. Now that you've got a cheat, you should be able to do these much faster. So work through the cheat. Do you want more time to work on it, or can we jump? A few seconds? I'm going to take that as a yes. So, what made these two more difficult than the previous two? There's a lot more pi bonds, right? Okay. Both cases we have multiple pi bonds. In the first one, I have a benzene ring. Does the benzene ring, any of the pi bonds in the benzene ring act like an alkene? No. So you do not touch benzene rings. Okay. Only at the end of the semester can we talk about dealing with those. So really all we're going to do is stretch our alkene. Okay. So that I get lazy, I'm just going to write pH. Go ahead and erase out of the middle, drop in my oxygens. Now I want to evaluate, do I have hydrogens? Do I have hydrogens? Yes, so what do? I replace them. My acids. Yeah? Everybody get those two answers?
So these are essentially two separate products.
We end up with two separate products, which is a very common question. If you take a look at the practice exam, there is a question like this. How many products do you get? Okay. And it is a common ACS style question. We don't care what the product is, just how many do you get? They tend to show up with cleavage reactions because, well, there's multiple products. Okay. So you have to be careful to watch out for rings potentially changing your answer. The other one that's dangerous is terminal pi bonds, because it is very common for students to just delete that carbon. Is the structure on the right here still an organic molecule? It has carbon, so it still holds to our definition. We have to include it. So this would be two products. Okay? Gen Chem review. Okay? Because Gen Chem doesn't like structure because they think structure is irrelevant. They're horrible people for it. They're not horrible. Second product is also written as H2CO3. Anybody know anything about H2CO3? It decomposes into CO2 and water. What are your two products? Product number 1, product number 2. You don't get the bicarbonate or the carbonic acid. It decomposes into CO2. Are you responsible for knowing that? Were you supposed to have known that back in Chem 130? For those of you who didn't take chemistry in this state, that would be fundamental chemistry, like Chem 101. Yes, you were responsible for it then, which means you're responsible for it now. Okay? So you do need to acknowledge that that chemistry is there. Second problem. What makes the second problem more difficult? Triple bond. And? Is it a benzene ring anymore? No. What does that mean about those pi bonds? They can chemically react. Which means when I go through to draw this out, I'm going to have my stretch double bond, my stretch double bond, connect those. Whoops, that was... Seriously, you're going to laugh at my drawings. Game on. I'm going to make you show me all your work from here on out. Stretch the triple bond. Right? What do we go through and do? Erase the middle out of them, drop in your oxygens. Draw my oxygens. Add hydrogens. Now what do I do? Whoops. Yeah, almost. What's that? Did I mess with the alkyne? I did. There's no longer an alkyne. Okay? So you may not like what I've got drawn, and we haven't gotten there yet. So what we do is it's a nonpolar pi bond. Permanganate will cleave the triple bond just like a double bond. So I have erased the middle out of it and put in 2 oxygens. Okay? And yeah, we can address that in a second. Let's look at the other half. Okay? What happened to those hydrogens? They need to get replaced with oxygens. So we get my OHs, OH, OH, OH. We don't like the triple bonds. What's really going on over there? Triple bond to oxygen would mean I'd have a positively charged oxygen. Does that make sense? No. So what happens is we can trade and add another oxygen. Okay. We still need to replace each and every single one of the bonds of the alkyne or the alkene with oxygens. Okay. That has to happen. Okay. But it doesn't have to be the same oxygen. What happens with the last one? Whoops, that's a big eraser. We could also go here, but with that hydrogen, what happens? OH, which then means CO2. How many products do I get? I get 3 products out of this. Okay, so there was a question for seeing the shortcut again. Are we covered with that? Yeah, we're good. And then, because of the strong oxidizing power of permanganate, okay, that's going to be the simplest answer. Permanganate is such a strong oxidizer that it is going to completely oxidize the structure. So any hydrogen that is on that carbon that is reactive will get replaced with oxygen because of permanganate. Okay. The slightly longer answer would be looking at the mechanism, which you asked about. We went through it blazingly fast. Okay? And then the really long answer is probably looking into quantum mechanics to explain the reactivity of permanganate versus carbon in oxidizing states, which brings back 152. Which, by the way, I can't do. I can do all the other parts, but I can't do that last part. Okay? Kind of makes sense? Okay. The last kind of cleavage oxidizing agent is ozone. Again, it's the same pattern. It's oxidative cleavage. It goes through and it'll do the same thing. We end up with carbonyl. So if we go through and count our carbons, our starting structure at the top, 1, 2, 3, 4, 5, 6, 7. And we look at our product, 1, 2, 3, 4, 5, 6, 7. Exact same process, or exact same principle is a better word for this. The mechanism gets really nasty. So for those of you that are interested, by all means, feel free to take a look. The first thing we form is the malozanide, which is straightforward. That's exactly what we've already talked about. Okay? That's that cyclic ring. Malozanide, as you might expect, is highly reactive. Why might it be highly reactive? What's that? Why is it unstable? Oxygen bond to oxygen, not just one, but two. Malozanide, very unstable. That thing goes through this giant cluster F of elimination reactions to kind of stabilize out, which still has an oxygen-oxygen bond, which then does all sorts of intramolecular nastiness to get you to the ozonide, which is also equally reactive because it still has one oxygen-oxygen bond, but at least we neutralized one of them. Okay? The ozonide is somewhat stable, okay? Just like peroxide. Okay? It'll hold for a little bit. Depending on what we add next, we get two different products or two potential pathways. Okay? In this case, we're adding dimethyl sulfur, okay, or dimethyl sulfide, commonly abbreviated as DMS. If you go through to look at the products, okay, what is interesting about this product as being distinct from the permanganate reaction? Okay? The permanganate reaction could get ketones. That was perfectly fine. You didn't have to go to a carboxylic acid. What did we do once we did the cleavage? We looked for hydrogens connected to the carbons where we did the reaction. Is there a hydrogen there? Yeah. In permanganate, what happens? Turn that into an oxygen. It becomes a carboxylic acid. What happened in this case? Ozone didn't go there. Why not? Okay. This has 3 oxygen in malozanide. I only have 2 in the product. What happened to the 3rd oxygen? Okay. As a secondary product with what? This is dimethyl. So 2 methyls, sulf, oxide. DMS becomes DMSO. Okay? DMS will scavenge one of the oxygens from the ozonide so that we do not form the carboxylic acid. We stall at the aldehyde. Okay? Why is that important? Well, is the reactivity between a carboxylic acid and an aldehyde different? Yes, that's why it's important. If I want to stall at the aldehyde because I need the aldehyde functional group, permanganate is an awful reaction to run. Okay. Ozone would be excellent because I can stop at the aldehyde. And really all that's happening is that I've added a reducing agent to stop the oxidation, okay, which sounds really, really weird. We look at the very beginning of this reaction. Okay. There's our starting material, and we go all the way to our final product. What kind of reaction did we do? We did an oxidation, but what did I just say we added? A reducing agent. Am I still oxidizing? Yes. Why am I adding a reducing agent? So I stop the oxidation. Okay, so what you will see referenced, hopefully, of course it's not on the next slide. Let's see, is it soon? Sorry, that's me trying to find it. Close your eyes if you get dizzy. Please don't throw up. Oh, geez, it's way back there. Sorry, guys. Whoop. Here's our ozone, and our spider diagram comes out. There's our malozanide. And then we say step 2, we call it reductive. So am I doing a reduction from the malozanide to the final product? I'm reducing the amount of oxygens to that compound. Am I really? There's 2 bonds to oxygen, 2 bonds to oxygen. As far as the carbon's concerned, I'm not really doing anything. Why are we calling it reductive? Because I'm getting rid of one of those oxygens. Okay, I'm just kind of cleaving it from the system. Okay, it is not a reduction reaction. It is just not as oxidizing. As opposed to the other condition, which is just let it go, do whatever it wants. And what happens? Full oxidation. Okay? So this is a classic pathway differentiation, typically referenced with DMS. I have also seen zinc and water as a potential reagent to do the reductive. It is typically shown with DMS, and it can be written as the chemical formula or as the abbreviation DMS. Okay? I want you to be aware of that because that's a big trigger point, a big differentiator for the ozone pathway. Was there a question maybe, Mo?
Yeah.
Sorry, close your eyes again. Okay. So in our control of ozone, we get two conditions. We can either do the reductive condition, which is with DMS, or we can do it as oxidative. Okay. This gets a bit misleading. I would love to say we're consistent with the secondary reagent for the oxidative cleavage. We're not. I've seen water. I've seen nothing. I've seen peroxide. Okay? So really, again, the big trigger that allows you to say this is going the reductive pathway is looking for something like DMS. Okay? If you see nothing else, you should be assuming that you go the full oxidative route. We need to drop that all the way down to the acid. Why does the other one not go to an acid? Okay, for those watching at home, why is this carbon not becoming a carboxylic acid? There's no hydrogen connected to it. It can't become an acid because it's connected to carbons. While permanganate is an awesome oxidizing agent, it can't break carbon-carbon sigma bonds, right, on their own. It has to be breaking carbon-hydrogen bonds. Okay. Are there stronger oxidizing agents? Permanganate is a strong oxidizing agent, and even here it would end at the same thing. Okay. What's the difference between permanganate and ozone? Okay. Permanganate and ozone differ based on control. Permanganate, no control. You oxidize. Ozone, there is control if you have DMS. Okay, DMS or that zinc water system. Okay? I want to say I was asking a question before that, but I don't remember what it was.
Is there a stronger?
Oh, is there a stronger oxidizing agent? I mean, oxidizing agents, those are pretty dangerous, right? Anybody breathing in this room? Yeah, what are you exhaling? Carbon dioxide. Where'd that carbon come from? Sugar came from a carbohydrate. Your body is constantly oxidizing things. Okay? We can react sugar with oxygen in the air. Oxygen in the air is a strong oxidizing agent. That's why what happens when you burn sugar becomes CO2. Okay? That is our final oxidative state. It does not become caramel. Okay, burn. Okay? Kind of neat, in my opinion. Our reduction reagents, we're adding hydrogen. Okay? Again, we're adding these only to the non-polar pi bonds at this stage, so don't stress about polar pi bonds yet. Okay? All of the reagents are listed. Okay? The very first one is entirely non-selective. What does that mean? Okay, it reduces anything with a pi bond. Alkenes, alkynes, and it just goes. Okay? H2 and rainy nickel. It's actually even less selective. Okay? H2 and rainy nickel will just destroy things. Okay? H2 and Lindlar's catalyst. Okay, this is where we bring in stupid names. Well, not stupid. I'm sure it was a nice name. Lindlar's catalyst is also known as Yep, I have. Thank you. At least for acknowledging that. Poison catalyst. Sometimes you'll see barium sulfate, calcium carbonate maybe. Okay. And we need the actual catalyst part. What's the catalyst part according to the top two reactions? A metal. Okay. It's usually platinum or palladium. Okay. Barium sulfate and calcium carbonate bond to platinum and palladium, and they bond in such a way that alkenes cannot bind. What does that then mean? So the first thing I'll put in, it is selective. What is it selective for? That's getting at the end result, not what it's selective for. If it can't react with an alkene, what must it react with? Alkynes. Okay. The sodium in ammonia, okay. Fun, goofy, crazy mechanism. Also a selective one. Selective for alkynes. Okay. Why do we have multiple non-selective reagents? One fair answer, because I told you. It turns out they do have some selectivity, but it's hard to modulate. Okay? So you will see sometimes reference, particularly in the textbook, where they say, well, if we go with hydrogen at 50 atmospheres versus hydrogen at 30 atmospheres, it reduces a different thing. How many of you really want to care about the pressure of the hydrogen in your reaction? I'm going to guess by the lack of hands. Memorize them as non-selective. They will hit anything. Okay. H2 with Lindlar, and sodium with ammonia. Why do we have two different selective reagents? Okay. These are selective for alkynes. What does that mean? What would they produce? Alkenes. Is there something different about the chemistry of an alkyne versus an alkene? Hybridization of carbons, fair enough, didn't consider that. That is true. Alkynes, because of their hybridization, are linear. Alkenes have the option for cis and trans, which means depending on the mechanism, be it Lindlar's catalyst or the sodium and ammonia, we could end up with different orientation products, cis via trans. Okay. Turns out we do. For our quick memorization, the sodium and ammonia is trans product, okay, or an anti-addition. The Lindlar's is a cis product or a syn addition. Okay. With that, we're going to delete it all and go right back to the very beginning. When we're talking about our metal catalysts, we have a metal surface that brings the hydrogen close to the pi bond. Hydrogen is too small of a molecule. It cannot physically reach both carbons. Okay? If it can't reach both carbons, then a bond would have to break so that it could then get to the other carbon. But then that means, what do I have floating around? Okay, one option would be an acid. I would argue it's actually not going to be an acid, because we've got our two carbons, and there's our hydrogens that can't physically reach both. Right? If we said this reacted, how does the alkene react? It attacks, which then means what would be floating around? Hydride. Hydride isn't a stable molecule to float around on its own. Okay, so it can't happen in this fashion. Okay, at least with the boron structure, boron slightly larger, it helps to bridge that gap. Two hydrogens can't bridge the gap. So we need an intermediary to help bridge that. That's the metal catalyst. Okay? And in particular, when we're talking about the metal catalyst, we're talking about platinum, palladium, or nickel, not sodium. Sodium's a different mechanism. Okay? So the hydrogen and the alkene or alkyne coordinate to the platinum surface. Once attached to the platinum surface, They can float around on the surface until the hydrogen gets close enough that it can react, breaks one of the interactions of the alkene to the surface, and the other hydrogen slides in. In this case, the reaction happens so fast that what happens to that intermediary, I know it's insanely tiny there, can that happen, that rotation? Okay, bigger. Can that rotation happen? The answer is no. It can't happen. What does that mean? So it's not a double bond. It's saying that this reaction of the hydrogen then transferring to the next position happens so quickly that we do not get rotation. What does that mean for us?
Why? Because it's stuck to the metal?
I honestly don't know the why, so I can't answer that for you. But being connected to the metal is not a bad idea. What does that mean?
Then it has to be on the same side?
The hydrogens must be added on the same side. So we are getting a Syn addition for both of these. I talked about it in first semester, so everybody that didn't have me in first semester didn't get this. What's the difference between Syn, versus cis? Okay, everybody in first semester gets to try now. What's the difference between Syn and cis? And that Syn is S-Y-N. Why don't we just call it one thing? Be done with it.
The mechanism versus the product.
They're looking at different things. A Syn addition, the Syn is acting on the verb of addition, which means Syn is an adverb. A cis is acting on a product. The product is a noun, so cis is an adjective. Right? Why do we have two different descriptors? Because they're describing different things. Right? Welcome to English. Okay? So you may hear reference to both. Typically, it is referenced as a Syn addition. You typically do not hear people reference it as a cis product formation. Okay? So just be kind of careful with that terminology. Why does this become important? Well, if you had a cis or trans double bond, when you add the two hydrogens, they're added on the same side. The stereochemistry is now locked, and you have to be careful with the arrangement of your products, wedges and dashes. Okay, so you have to be very, very careful there. When we move to Lindlar's catalyst, the only thing that's different about it is we have the same thing, except a catalyst gets up in here, and it chases alkenes away. Okay, very sciencey. Go away. Okay, we only get the alkyne. Okay, because the root of the mechanism is still the same, we still get a Syn addition. So what kind of pi bond would we end up with? Because, remember when we're doing these two reactions, the bottom two, they were selective. They were selective and only reacted with what? Alkynes. What kind of alkyne would I get if I ran a Syn addition? Or sorry, an alkene would I get? I end up with the cis alkene. Does that seem kind of weird? Yes. Why? What can you tell me about the cis product? It's less stable than the trans product. It's higher in energy. Right? Why does it then form? Because the mechanism forces it to happen that way. It's how those hydrogens are added to the pi bond. Okay, so we don't get a choice. Okay? The next fun one comes in with the last one, are sodium and ammonia. Okay, so all of this is talking about the alkynes. Okay. What happens with sodium and ammonia? Okay. One thing that I do want to address here is that sodium and ammonia is not sodium amide. Okay? And if you're like, okay, that's not that big a deal, how do you make sodium amide? by mixing sodium with ammonia. Okay. Just want to put that out there for the record. Different reagent, they do entirely different things. What's the reactive species? Alkyne, sodium, ammonia. Okay, we might go with the alkyne. Has anybody seen potassium thrown into water? It's very reactive. It's very explosive. What do you think happens with sodium when it's thrown into water? Same thing. How come whenever I flex my muscle, it's not exploding? Because you don't work out. No. What's our difference? What is it? Do you even lift? Sorry. Those are the ions, sodium and potassium ion, not the metal. What are we looking at here? The metal. It's the solid. What makes sodium reactive? If it's in its elemental state, its electron configuration has how many electrons? Just one. Does sodium want to have an electron? No. How do you know that? We could go with it's a metal. We could go with insanely low electronegativity. What charge does sodium always have when you see it? +1. All of those lead to the same thing. It doesn't want the electron. So what does it do? It gives it up. Okay, what does it give it up to? The next highest energy electron. Where's the next highest energy electron? The pi bond in the alkyne. We can only move a single electron, though, because sodium only has one. Because the alkyne had 2 electrons in a single pi bond, where does the other pi electron go? To the other carbon. We end up with this glorious-looking structure. I wish that's okay. I have a bond between carbon and sodium. That's probably not true. What does that roughly equate to? An ionic bond. Does carbon want to be negative? No. What does it need? Positive. Where's there a positive? Radical is not positive. From the hydrogen from our solution, and we would end up with okay. Is that structure stable? No, why not? It's a radical, so what does it want? Another radical. Where do we have radicals being generated from? Sodium. So what happens? Another sodium. What's the result? The sodium connected again. Do we want sodium connected? No. What happens? We can look at the ion form, picks up another hydrogen, and we'd end up with our product. It is this transition that becomes super important. Okay? When I form that negative charge, where do I want the R groups to be? Opposite sides, because trans is more stable than cis. Because I'm never directly coordinating to a metal center, okay, or a metal surface, I can get the transformation. For those of you who think that that looks ugly, draw it yourself, or just look at that. Okay, there's the prettier version of it, doing the same thing. It gets a little bit weird. Okay? I saw some faces in there. Number 1, because we had radicals. Yay! Number 2, what did we end up with? Radical and an anion. Yay! Cool stuff. Okay? Sodium does some neat, crazy things. This is why we don't eat sodium metal. Okay? Bad stuff happens. Okay? The end result is that we end up with the trans double bond. The hydrogens went on to the structure in an anti-addition. Yeah?
Is this a wiggly R bond representing like a bond and a half?
Nope, that's still a formal bond. What does the wiggly represent? It represents that we haven't specified the stereochemistry, okay, or its orientation left or right. Okay, you'll notice that I did specify it here. That's actually bad. It shouldn't be specified yet because the hybridization there is still officially sp. It should still be linear. The lone pair doesn't count as a pair of electrons. Okay. So it's really only at the very end do we force the trans configuration. Okay. This chemistry is so bizarre that somebody else decided to use it too, and they threw it on benzene. But benzene doesn't react. That's how reactive sodium metal is. It actually causes benzene to react. Okay? We will talk about that reaction at the end of the semester. Don't worry about it right now. Okay? Using sodium metal and ammonia is sometimes referred to as the Birch reduction. I believe when they reference it as the Birch reduction, they're talking about reducing benzenes. Okay? Believe it or not, we actually got about as far as I wanted to get to today, so it's pretty awesome. We still have a little bit of time, so we are going to continue going. Yay! Chapter 10. Okay? Chapter 10 is now a new chapter, and it's going to be, I think, the end, okay, as far as content for Exam 1. I really don't feel comfortable moving fully into Chapter 13, which is all about synthesis. When we talk about Chapter 13 as synthesis, there is very little for me to lecture on. Okay? It is a read the textbook to get what the textbook thinks about how you should solve synthesis questions. That's all Chapter 13 is. We will work through an activity in class that helps kind of get at that and help remind you of the reagents. We will do that activity next Monday because it'll work as a nice summary to help bring in some of the reagents we've talked about this semester, okay, and help you review for the exam. Okay? So we will see that and we will talk about synthesis, but any question on synthesis in the practice exam at best will show up as extra credit. It will not show up for raw credit. Just want to clarify that. Make sense? Is anybody like, oh, I want it to be tested on synthesis? I'm just curious. Most people hate it. Okay. So Chapter 10 is substitution elimination. So the stuff that you learned in first semester about substitution elimination was very, very general. We didn't get into details. Chapter 10 now goes through and says, if I want to do this substitution, this is the reagent I want to do or use. Okay? And ultimately, to me, I went through and categorized what I saw within it. So the first one, make better leaving groups. Okay? That's ultimately the biggest part of this chapter. We're just making better leaving groups. I don't like that leaving group. I'm going to make it something else. Okay? Make better nucleophiles. Okay? In that case, we're looking at epoxides and is in quotes oxetanes. Oxetanes is the larger category of ring structures that have oxygen in them. Okay? Epoxides is our primary focus. We'll look at amines and their substitution. We'll look at amines and elimination. And then how do we make better nucleophiles? This is the fun one to me, alpha carbons. Okay? Alpha carbons is pretty much where we're going to be spending the rest of the semester. Okay, so it's a nice lead into the rest of the chemistry for the rest of the semester. Okay. With that, I said I was going to talk more, but that was all I did. It was just kind of review. So we can be done there, assuming you're okay. Yeah? Okay.